the time of year because I haven't really had much problem before now. All right. Same. So I've got this thing and I looked at it and there's the biggest difference between pre-calc and calc is that pre-calc always talks about average velocities. Okay? In other words, this question number 1 you did by rise over run, right? It's the slope of that line. It's 120 divided by 2. That's how you got the average velocity. And that's the only thing you're familiar with at this point, is average velocity. And you may not have put it together with slope, but that's what it is. It's rise over run. It's as simple as that. And this equation you wrote here, 60h equals y, well, that's y equals 60h, has a slope of 60, right? And a y-intercept of 0. So it fits that perfectly. Now, what would the graph of the velocity look like? Well, they've told you in problem 1 that it's a constant velocity, not a variable velocity. Well, I want to see anybody drive from Denver to Cheyenne going exactly 60 miles an hour the whole way. Won't happen. It's not a real life problem. Sometimes you go 40, sometimes you go 70, sometimes you go 52. So this is an idealized problem. You're not going to travel 60 miles an hour exactly the whole way. But in terms of average velocity, yeah, this is a great graph. You averaged, there's only one problem with this graph. Let me point it out. What's the problem with it?
What?
It should only go up to the number 2.
Oh, okay.
In other words, this trip did not take 3 hours. It took 2 hours. And that horizontal axis is 2 maximum. In other words, this part of the line, I don't know if you can see where I'm pointing, this part of the line shouldn't be there. So erase that part.
Okay.
Okay. I need to give you a 20-minute lecture on slope of the tangent line, because that will tell you the difference between precalculus and calculus. In other words, the average velocity is not the same as the instantaneous velocity. Okay? Let me just give you a preview. I'm not going to spend a whole lot of time on it at the moment. We'll go through these problems, make sure you get through them all. But just to tell you what I'm talking about, if I have a position curve like that, okay? In other words, I'm talking the equivalent of the first curve, where it's your distance. This is the distance you've traveled. This is the time you've taken. That's called a position curve, okay? So if I wanted to say how far I've gone between hours 1 and 2, that would be f of 1. That would be f of 2, correct? Whatever that function is, I don't need to know that function. I just need to know that it's a function. Calculus is all about manipulating functions. Just like arithmetic manipulates numbers, and algebra manipulates variables that represent numbers. Calculus is all about manipulating functions. So you need to think of it in terms of a function without knowing what the function is. Now, if I said, what was your average velocity in between hours 1 and 2, what would it be?
I don't know.
Well, it'd be the slope of that line. And the slope of that line is f of 2 minus f of 1, that's the rise, over the run, 2 minus 1. So your average velocity is always pretty easy. In other words, there's no calculus involved. But what if I asked you, what is the velocity 1 hour in? Well, that's instantaneous velocity. And you can probably see the problem is we're going to have f of 1 minus f of 1 all over 1 minus 1. In other words, we're going to have 0 divided by 0. How the heck do you figure out instantaneous velocity from that? Well, calculus came up with, and this was actually Sir Isaac Newton that came up with this method. And it's a beautiful method, and you definitely want to understand it. Okay? First of all, you got to understand that curve, that equation right there. You have to understand that average velocity is the slope of the line, rise over run. The rise is the difference between F2 and F1. And the run is the difference in the 2x measurements, 2 minus 1. Okay. Well, if I said, what's the velocity right there? Well, average velocity, the rise over the run is going to be 0 over 0. You can't figure out average velocity, not with conventional algebra. You have to use calculus. And this is how they do it. And this is what this whole first page is all about. It's trying to get you to understand how you go from average to instantaneous. Let me draw this thing again, just so you are with me here. A little bit bigger. Now, what I want is the velocity at that point right there. Well, I know that the average velocity between those 2 points, A and B, is the function evaluated at B minus the function evaluated at A all over B minus A. So average velocity is f of B minus f of A all over B minus A. That's rise over run. You with me?
Yep.
Okay. Now here's what we're going to do. And this is the calculus part. We're going to figure out what the slope of that line is. And then we're going to figure out the slope of that line. And then we're going to figure out the slope of that line. And what we end up with is the line that is tangent to that curve. That's the instantaneous velocity. Okay? And I don't want to lose you here, but there's few lectures in calculus that are more important than this, the slope of the tangent line. So if I want to know what the slope of that tangent line is, now let's call that x. Let's call this x plus h, making that distance h. With me?
Mm-hmm.
Well, what's that line? That's f of x. This point over here is f of x plus h, right? So if I want to turn this into a calculus problem, I've got the instantaneous velocity is f of x plus h minus f of x all over x plus h minus x as h goes to 0. And you see why that, in other words, if I take this measurement h right here and I reduce it and I let it go to 0, well then this line that I've drawn here becomes the slope of the tangent line. And that slope of the tangent line is the instantaneous velocity. Okay? And if you wanted to describe differential calculus in 2 words, those would be the best 2 words to describe. Instantaneous velocity, or really more precisely, instantaneous rate of change. Notice that this function that I have here changes differently depending on where you're at. Right here, barely changing. It's rising a little bit. Right here, starts rising a little more. Right there, starts rising a little more. Wow, by the time we get up to here, it's rising very fast. All of those can be measured by the slope of the tangent line. There's the slope there. There's the slope there. The slope there is a little steeper. The slope there is really steep. So the steeper the slope of that tangent line, the faster that function is changing. All right. I don't know how much of that sank in, but let's go back to your problems here. I'm not in love with the way they start you out here, but I'll live with it. Got 2 just fine. In other words, you figured out. Now, notice the difference between 1 and 2. Or actually, this curve here, that's a position function on the vertical axis. That's how many miles you've driven. On the horizontal axis is time in hours. Okay? And now, when they want you to draw this graph, the vertical axis is not distance, it's velocity. The horizontal axis is still hours, time in hours. But what this is saying is that you started at 60 miles an hour, you went 60 miles an hour the entire 3 hours, it was only 2 hours. That's why you need to change that. Okay? All right. Now, let me just point out one other thing. If you take your position function, what's the slope of that thing? It's a straight line. Has a constant slope everywhere on there. What is it?
The slope of the line?
It's rise over run. What's the rise divided by the run? What is it?
Just over 1.
What is it?
60.
Yeah. Well, notice that's what the velocity is 60. That's not accidental. In other words, velocity is the slope of the position function. What we're looking at up here is the position function. That's how far. At the end of 1 hour, you've gone 60 miles. At the end of 2 hours, you've gone 120 miles. Okay? And you really probably shouldn't have that arrow right there either, because it doesn't say you went beyond Cheyenne. It says you went to Cheyenne. So I would erase that little arrow after the dot. Okay? And this second graph is the velocity graph, which is the first derivative of position. Now, I know you don't know what the word first derivative means yet, but the first derivative is the instantaneous rate of that function, the instantaneous rate of change. And that's the slope of this thing. So this thing has a constant slope of 60. Whether you go out 1 hour or 2 hours, the slope of that line is 60. Well, that's what the velocity is. It's 60. It's a constant 60 miles an hour. So keep that in mind. Velocity is the slope of the position function.
Okay.
Now, this is good. Here we're back to position function. Position, in other words, the vertical axis is the total distance you've traveled. Well, in the first hour, you traveled 60 miles. So you stopped for lunch, so you didn't travel any during this period here. And then you started back up again at a constant rate of 60, and you traveled another 60 miles. So this is totally correct. Find a rule for the equation. You'd have to present it as a piecemeal function. In other words, it's y equals 60h to there, and then it's y equals 60 from there to there, and then it's again y equals 60h from there to there. So the equation at this point really isn't that important. Now notice that they're asking us to go from this position function at the top to the velocity function. And there's only one thing I would quibble with this about. Need a line right there.
Okay.
Right? In other words, between hour 0 and 1, you went 60 miles an hour. But between hour 1 and 2, you went 0. You can't just leave that out. You went 0. So this line needs to be there on the x-axis. And then between hours 2 and 3, you went 60 miles an hour again. Now, the next question is extremely important. It's almost the essence of integral calculus. It's really only two forms of calculus: differential calculus and integral calculus. You'll focus mainly on differential calculus this year, but you'll get into a little bit of integral calculus. Okay? Differential calculus can be summed up in 2 words: instantaneous slope, instantaneous rate of change. Sorry, 4 words. Integral calculus can be summed up in 3 words: area under the curve. If I want to take this graph and I want to figure out how far we traveled, I figure out the area under that curve. What's the area right there?
That would be 360.
Hold on. Area is base times height.
Oh, yeah, no, it'd just be 60.
It's the area of this on the right side.
60.
Add them 2 together, you went 120 miles. So this is an important principle to know, although not so much this early on, but if you want to know how far you went, you take the area under the curve.
Okay.
Let's look at this one down here, just skipping ahead. If I want to know how far I went in 2 hours, the area that under that curve. If I want to know how far I went in 3 hours, it's the area under that curve. Okay? Now, one thing you have not learned, you've learned in geometry how to figure out areas where everything is a straight line, right? Or a circle, but not curves like this. In other words, you have no information as to how to find the area under a curve. You haven't been taught it yet. That's integral calculus. In a nutshell, if I were to look at this picture down here, that's the position function. So, sorry. I was actually wrong. I'm ahead of myself on the area under the curve. Let's go on. It's hard for me to not talk about integral calculus because guess what? Integral calculus is the inverse of differential calculus. Precisely the inverse. Just like all other inverse functions you've learned about?
Yeah.
That's what it is. And you would have no idea from these examples that one was the inverse of the other. At one time, they were both treated like two separate, completely independent mathematical disciplines. Sir Isaac Newton was working on one, and Leibniz was working on the other. They had no idea that they were working on opposite sides of the same coin. They just had two different maths that they developed. This is in the late 1600s. And it wasn't for quite some time after that that they realized, wow, these things are actually the same thing. It's just one is the inverse of the other, which was a huge discovery because then it gave them a way to figure out the integral of a function. All right, let's go back and go through these. I want to make sure you can do all of these properly. Okay. So, you're correct with your answer here. In other words, we went on our trip. Hold on. And we advanced. What's happening right there?
He's just
stopped.
Heading to the end.
We stopped.
Yeah.
There's no velocity. In other words, the position is not changing. Keep that in mind. Very, very important principle in calculus is that when the slope of that tangent line is 0, which it is, those are key points on any function. That means the function's not changing at that point. So if it's a position function, your position's not changing. Well, the only way your position can't be changing is if you're stopped. And then you correctly surmised that during this portion of the trip, we went backwards. In other words, we missed the McDonald's cutoff at Fort Collins, and we had to backtrack for 10 miles in order to get back to it. And then what happens here?
They stop again.
Okay, turn around. In other words, you can't go from one direction to the other direction without stopping. I mean, ignoring for the moment, you could take a circular path, but your direction in your velocity in one direction has to go to 0. regardless of whether you take a circular path or stop, back up, turn around. But the fact is your velocity towards Cheyenne is 0 right there. Then you continue on your trip and you keep making progress, and you eventually, after 3 hours, reach Cheyenne. Well, you can see pretty easily here that if I didn't back up for an hour and stop, I'd have gotten to Cheyenne in 2 hours, right? In other words, if I take this part of the curve and just go straight to there, I'm going to Cheyenne. I'm doing 120 miles in 2 hours.
All right.
Okay, let me read, trying to make out your answers here. Hold on a second. Just make my way through this. All right. This is probably the key part right here. Let's talk about this next question. Of course, to me, there's so many key parts of calculus, but remember what we're looking at here. That's a position. I don't know what my velocities are. But what I do know about my velocities is that it's the slope of the tangent line. Okay? So if I want to graph my velocity curve with time, and time is almost always the horizontal axis when calculus is being done. Okay? What's my starting velocity? Right here.
What? Oh, sorry. I was just rechanging this.
Slope of the tangent line at that point right there.
0.
No, if I draw a tangent line, what's it look like? It looks like that, right? What's that slope? About 60. In other words, if I were actually to do the math, that would be about 60. So my velocity starts out at 60. There's no 0 point even. In other words, quite impossibly, your car went from 0 to 60 without going through any of the other speeds, which is impossible, but immaterial at this point. So there's one point on my velocity curve. I was going 60 miles an hour to start out with. Well, that slope of the tangent line stays pretty much that through 30 minutes. So through about the first half hour, that's what the velocity curve looks like. Now, what happens at 1 hour in terms of velocity?
They're completely stopped.
Okay, so I know this point's on the curve. So this curve must look like something like that. Okay, and now what happens between 1 and 2 hours? Is velocity positive or negative?
Negative.
Correct. So it's below the x-axis. And it's the slope of that. Well, that slope doesn't look as big. We'll call that a slope of 30. We'll pretend that you drove at 30 miles an hour when you were going back to the McDonald's. So you rapidly get down to 30 miles an hour until at the 2 hour mark, what happens?
You're stopped again.
So it's back to 0. So that point has to be on the curve. And then finally, the slope of the tangent line increases and gets faster and faster. So there is the graph of the velocity. And that's what they're asking for here, the velocity versus time graph. start by saying, are there any times where the velocity is 0? Well, yes, there is. There's at time 1 hour and there's at time 2 hours. And is all we have to do to fill in all of the other points is to figure out the slopes of the tangent line. When you draw a velocity curve from a position curve, you're basically drawing the slopes of the tangent line at every point along the horizontal axis. And that's what I've tried to do here. And this can be pretty confusing. I mean, it really takes a while to get used to this concept. Notice that at the very first point right there, my slope isn't 0, it's about 1. Well, it's about 60, because a slope of 1 here is 60 divided by 1. Okay, so my velocity starts right out at 60. And then clearly it's got to fall. I know that at 1 hour it's 0. So I got to go from 60 to 0 in that first hour. And the only way to do it is just to draw the curve like that. Then I know that it's negative. Notice my velocity curve everywhere from 1 to 2 hours is negative. Forget the fact that it goes down and back up. The fact is that it's in negative territory the whole way. And that's what that is negative territory the whole way. I'm doing negative velocity that whole time. Finally, I stop again, so this point has to be on my velocity curve. And then I start speeding back up slowly at first, and then faster until finally I'm going once again at about 60 miles an hour. And this curve probably goes like that, because you don't go faster than 60 miles an hour. You just get back up to 60 miles an hour.
Oh, yeah.
This relationship between position and velocity, extremely important. Then you have acceleration. And guess what? Acceleration is the slopes of the velocity curve. From a calculus point of view, you have position, which is usually represented by that. You have velocity, which is the first derivative of position. And you have acceleration, which is the second derivative of position. And that's how you get all three of those. Velocity is the slopes of the position. Acceleration is the slopes of the velocity.
Okay.
What acceleration is. When you're in a car and you accelerate, what are you doing?
Getting fast.
Well, you're speeding up your velocity. When you go from when your speedometer goes from 20 miles an hour to 60 miles an hour, it required acceleration. You had to increase. You didn't go instantly from 20 to 60. You went 20 and then 25 and then 30 and 40 and then finally you got to 60. And that's another rule of calculus, that you necessarily have to go through all of those points. You cannot go from 20 to 60 instantly. You can't go from 20 to 60 without going through 32 and a half. Let me put it that way. Okay? That's the mean value theorem. You won't learn it for a while, but as long as we're talking about it. Okay. Next question, is the velocity possible to be negative? And yes, we've already answered that. What is true about the graph when I am traveling the fastest? It's when the slope is the steepest. Excellent. We've already done this. In other words, that's what this, all my other writing was to create the velocity graph from the position graph. And remember what it was? I started at 60, went down to 1, went down below 1 to 2, and then went up again from 2 to 3. Okay. Let me redraw that and answer the next question. Well, that's okay. I can still redraw it. So we know this point was on the velocity graph. We know that point was on the velocity graph. We know we started at 60. And we know there was a period of negative velocity. And then we basically did something like that. How could this graph be used to find the total distance traveled? Wow. Hate the way they're teaching calculus. Hate it.
Mhm.
This is a question you should be getting 3 months from now, not now. The answer to this is the area under the curve. In other words, if I were somehow able to figure out that area, which is positive, and subtract out that area, which is negative, where you're going backwards in distance, and then to somehow add the area there, where you're going forwards again, and I added up all three of those distances, that would be the distance I traveled. And that will equal 120.
Okay.
And like I said, there's two things that it's worth knowing. Whether regardless of how long it is before you get to integral calculus, Chatfield does like to introduce you to the principle of integral calculus. And that principle is area under the curve. That gives you how far you traveled, as long as you're looking at the area under the velocity curve. You don't want to take the area under the position curve. That doesn't tell you anything. But the area under the velocity curve tells you how far you went. And you will learn a method where this curve might be given to you as a function. Let's say that curve is x squared minus 3 all over x plus 1. Some kind of curve like that. Okay? They're going to tell you how to figure out the area under that curve from 0 to 3. That's what integral calculus is all about. And that's why it's so important. Because frequently, that's an extremely important number. A lot of times in life, we know the velocity function, but we don't know distance. Let's say I had a beach that suffered from erosion. Okay? Every time the tide comes in, it takes away 1,000 gallons of sand. And so you're a tourist attraction, you don't want the sand eroding, so you put a machine on the beach that adds sand to make up for the sand that's being eroded away so that the beach stays stable. Well, the amount of sand I want to add is dependent on a lot of things. It's depending on the tides. It's when the tide comes in that it washes away a lot of the sand. So that's when I'd want to add it. Okay? But, so I'm going to add sand at a variable rate. It's not always going to be I'm going to add 2 gallons of sand per minute. Sometimes I'm going to add 2 gallons of sand per minute. Sometimes I'm going to add 15 gallons of sand per minute. Well, if I want to know the total amount of sand I add in any 3-hour period, guess what? I take the integral of that function and I can tell you exactly how much sand I'm adding. So calculus is used for problems like that. Whenever your velocity is variable. If velocity is constant, then you can use geometry. In other words, let's say this is the velocity, this is the time, and I have a curve like this. Okay, and there's 30, and there's 60. Well, if I want to know how far I go, it's the area of that trapezoid. I don't need calculus for that. I know the geometric formula for the area of a trapezoid, so I can figure out that area. Where calculus is needed is when that is a wavy line, like that. Now, figuring out the area under wavy lines is no mean feat. That is something that was only discovered 300 years ago. The Greeks and the Romans didn't know about this. So that was an extreme advancement in mathematics. And in fact, calculus is called the greatest advancement or the greatest development in mathematics in the history of mankind. Calculus is.
Mm-hmm.
And the reason is it allows us to answer so many questions that we never used to be able to answer. I never could have told you how much sand in total is deposited on that beach without calculus. Once you have calculus, you can answer that question. And you want to make sure that it's deposited at the same rate that it's eroding away at approximately the same time. So it's a key kind of question that is very common in the world. And there are literally thousands and thousands of them. All right, so the distance time graph, which was a position function, whenever you're plotting distance versus time, you're plotting the position of the car or the particle, right? So start thinking of this as a distance function. And distance functions are always given by s of t. So they're saying that distance function is a cubic, which you correctly surmised because it looked like that. That's what cubics look like. Okay? Now, the graph appears to contain the ordered pairs, which you correctly put in there. And you've mastered your calculator enough to know how to do this, or how'd you do the second part?
No, I just found the answer for that one. I had no idea how to get that.
Okay. What'd you use before this year? Did you use a TI-84 or an Inspire?
Yeah, I did. So I don't know. I don't have any idea how to use the Inspire.
Now, the Inspire is significantly different. It is a big learning curve from the TI-84. So be prepared for that. It's a much better calculator, much better, allows you to do a lot more things, easier. So it's definitely a step up, but it's a whole new operating system. It's probably the equivalent as if you went from an Apple to a Microsoft operating system. They're hugely different. So, but it's just an entry into the calculator. In other words, you got to put your 3 points in there, and you ask it to do a cubic regression, and it spits out that formula. Actually, what it spits out are 30 minus 1406 and plus 190. And it leaves it to you to put the variable in there.
Oh, really?
And maybe a constant. There could be a constant there also. But it's a cubic. Okay. Does this graph look similar? Yes. Okay. Now, how far from my starting point am I after 1.5 hours? Let's go back to this because I need to pull up this graph. This graph here was the graph they're talking about. So at 1.5 hours, hold on. That's right there. And yeah, your answer of 71.2 looks correct. Now, I'm assuming you got that answer by plugging in 1.5 for t. Okay. And that's the correct way to do it, rather than doing it visually in the chart. But it never hurts to check and make sure that it agrees with your graph. Okay? So yeah, that answer makes sense. I didn't plug it into that equation, but it matches the graph. How could I calculate the average rate of change of my position with respect to time during the first hour of my trip? Well, you got it right. I'm going to calculate the rise over run from here to there. Well, how far do I go? About 80 miles in that first hour. The run is 1. So if I want the average rate of change between 0 hours and 1 hour, I take the value of the function there, f of b, or in this case f of 1, and I subtract out the value of the function there, which is f of 0, and I divide the whole thing by 1. In other words, let's write this a little bit nicer. More understanding. Here's what it really is. The function evaluated at 1 minus the function evaluated at 0, that's the rise, correct? Over 1 minus 0, which is the run. And when you evaluated this function, this cubic function, at 1, you got 80. When you evaluated it at 0, you got 0. So, yeah, 80 miles per hour is the average rate of change. And always remember the difference between average rate of change and instantaneous rate of change. Average rate of change is an algebra problem only. It's not a calculus problem. How else could you describe this value? Average velocity, okay. Yeah, given the next part of that question, I'll go for that. How would you get the average value from 2.2 to 2.8? Give me the formula I'm going to use.
You're going to do f of 2.8 minus f of 2.1.
2.2.
Yeah, sorry. Over, just would it be 1?
2.8 minus 2.2.
Oh, okay.
This is the rise. This is the run. Average is always rise over run. The only reason instantaneous is difficult is because rise is 0 and run is 0. So you end up with 0 over 0, which is called indeterminate, and you can't really figure out what it is. And that's why calculus is needed. But for average, it's always that. And explain why you could not use the same procedure to find the instantaneous rate of change or the instantaneous velocity of my position at a particular time. And I just told it to you. In other words, if you wanted to find the instantaneous rate of change at, say, 2.2 hours, here's what it's going to be. If you try doing it the conventional way, it's going to be f of 2.2 minus f of 2.2, that's the rise, and the run is 2.2 minus 2.2. And what that gives you is 0 divided by 0, which tells you nothing. You got to use more advanced techniques to figure out instantaneous rate of change. And what it is the slope of that tangent line. Okay? Now, let's go further here. this is kind of an exercise here in getting very close to the point. In other words, they're wanting an instantaneous rate of change at t equal 1. Well, we don't know how to do that yet. Okay, in other words, I've told you that it's the slope of the tangent line, but you still don't know how to figure out that slope of the tangent line. You'll learn that all next week. Guarantee it. That'll be what next week is all about, is the slope of the tangent line. Well, maybe not. Maybe limits. Most calculus courses start with limits. And so far, you don't have any limits here other than this word right here, limiting. That's the key. All calculus courses start with limits. Okay? But if I wanted to calculate the average rate of change from 1 to 1.01, it would be what? F of what?
F of 1.01 minus 1, F of 1. Over 1.01 minus 1.
Just 0.01. Okay. And then you could calculate that number, right? Because you have the function. In other words, you can figure out what f of 1.01 is. You can figure out what f of 1 is. And you can divide the whole thing by 0.01. That's your average rate of change between those two times. You can do the same thing for that, smaller time interval. Notice that this only goes for 1/1000th of a second. Not over here, we're at 1/100th of a second. Well, and then finally, they want you to do what the average rate of change is in 1/10,000th of a second. Well, guess what? This approximates the instantaneous velocity the best. The smaller that interval is, this interval is 1/10,000th. This interval is 1,000th. This interval is 1/100th. The smaller that interval is, the closer your average rate of change is to the instantaneous rate of change. So whatever number we come up with there, that's going to be the closest thing we have to an instantaneous rate of change. Now, we're kind of running out of time, so I don't want to go through these calculations. I trust you can do those, though.
Okay.
I mean, you can, right? You're not confused about any of these for number 7?
No.
Okay. Just do f of 2 minus f of 1 divided by their difference in each of the 3 cases. Now this gets interesting. The instantaneous rate of change is the limiting value of these expressions as the time interval gets smaller and smaller. And that's why I said the one on the right, where the time interval was only 1/10,000th of a second, that's going to be closest to the true instantaneous rate of change. But what calculus is all about is letting that differential, which is at 1/10,000th of a second, go to 0. And when it hits 0, that'll be your true instantaneous velocity at time 1. Now, I don't know what that answer is there because we didn't go through all the math, but that's what slope of the tangent line does. As you get closer and closer to that point, the time gets shorter and shorter and shorter until it's approaching 0. And that's why the next subject you're going to study in calculus is almost certainly going to be limits. The thing is that people study limits, and their first question always, after about a week of limits, is, the hell do I need limits for? What is this used for? I can't even imagine what this is used for. Trust me, there are a million uses for the mathematical discipline of limits. So understand that when you're learning limits, that they are really, really important. And this one, this number 9 here, just so I can kind of get you through this lesson here.
Mm-hmm.
Well, what you'd want to do on number 9 is a similar process as you did on number 7. Find out what the average rate is between 5.5 and 5.501. Then find out what the average rate is between 5.5 and 5.5001. And so forth and so on. In other words, make that differential get smaller. And it's going to approach the true instantaneous velocity. Even though you don't quite know how to figure it out yet, you can estimate it. Because whatever that is, that's going to be a really, really good estimate of your instantaneous velocity.
Mm-hmm.
And finally, let's look at number 10 here. Just one more. All right, I'm just going to give this one to you. If I have a position function that is described as f of x, in other words, h of t equals this position function, I'm going to call it s of t, because that's what position functions are called, it's s of t. Well, if I want the instantaneous velocity at any point in time, it's s of x, and I'll call it t, plus h minus s of t all over h, and I'm going to find that the limit as h goes to 0. That's what instantaneous velocity is going to be. And
Okay.
you don't know what that really means yet because you haven't studied limits, and that's why I'm a little surprised they didn't start you out right with limits. But I guarantee you they'll get to it really quick. But notice what this process does is it duplicates what we did on those 2 previous problems. In other words, we had one time, and then we added a little bit and had another time. And then we let h get smaller and smaller and smaller. In other words, we let h approach 0. And if you happen to know what the function is, you can then use algebra to figure out the exact instantaneous velocity at time t.
Okay.
Okay. Calculus is going to be very, very challenging, Jake, but also very rewarding and very important.
Mm-hmm.
Boy, taking Calc AB, you must be one of the few juniors in your class.
Yeah, there's like 3, I think.
Yeah. Which gives you a chance to take Calc BC next year. And Calc BC is a huge feather in your hat if you can take it in high school. I mean,
oh, really?
when I went to high school, they didn't offer Calc. I didn't get Calc AB until my first year at Mines. I got Calc BC in my second year at Mines. So sophomore at Mines is when I got Calc BC, and you're going to get a chance to take it as a senior. But trust me, it's going to be very challenging to get there. I don't know that there's a harder subject in high school than calculus. Maybe AP physics, maybe AP chemistry, but that's about it.
Oh, wow, okay.
Okay. I don't know, are you taking either one of those?
No.
Good. Good. You wouldn't want to try to tackle 2 of those at once.
Yeah, I know.
So, but it will be a challenge, but I can certainly help you. I've done an awful lot of calc tutoring, and I feel I really understand it well, and just don't let yourself fall behind. I guarantee you, if you let yourself get behind on this, you're not getting caught back up.
All right.
Okay? All right, Jacob. I will talk to you next time.
Yeah. Have a good day.
You too.